So the dean of the ASBE School of Business is concerned that grades in an MBA program are distributed appropriately. Too many high grades or too many low grades could pose a problem. So we want to test the claim that the mean GPA of ASBE students is larger than 3.3 at the 0.01 significant level. So we have several questions here. First, to choose the null and alternative hypotheses, to determine if it is a two-tailed, right-tailed, or left-tailed test, to compute the test statistic, and then to state the conclusion on whether or not we would reject the null hypothesis or fail to reject the null. So starting up here, we're checking that the mean GPA is larger than 3.3. Now over here on the left, we have three sets of null and alternative hypotheses that are related to a proportion. Since we're talking about a quantitative variable here and the mean of that quantitative variable, none of these first three options make sense because proportions correspond to categorical variables. So that's not going to work. It's got to be one of these three. Of course, the first hypothesis, the null hypothesis, would say that the mean is simply 3.3. And then the alternative, in this case, is based on the fact that we're checking to see if the mean GPA is larger than 3.3. So the one we want here is going to say that the mean is greater than 3.3. So we'll check that one. If we were interested in knowing if the mean GPA was different from 3.3, we would choose this one here, the mean is not equal to. And if we were interested in the mean, if the mean is less than 3.3, we would choose this one here. Now, because it is, this option here is our set of hypotheses, we're looking at what's happening on the right end of the distribution. So in this case here, this is going to be a right-tailed test, as opposed to two-tailed, which would correspond to this alternative, and a left-tailed, which would correspond to this one here in the middle. Okay, now, based on a sample of 70 student grades, the sample mean was 3.35 and a standard deviation of 0.05. Notice that it's giving you information about the sample. You know nothing about the population, and so therefore we cannot assume that this standard deviation is equal to the population standard deviation, and so therefore we have to use a t-test. Since we do not know what the population standard deviation is, and we're not told that we know that, we must use the t-test here. So when we come over here to StatCrunch, in our stat menu, instead of using z-stats, because we don't know the population standard deviation, we use t-stats. We have one sample, we have a summary of the data rather than the data itself. The sample mean is 3.35. The sample standard deviation is 0.05, and the sample size is 70. We're running a hypothesis test where we're checking the null with the null being mu equals 3.3, and we want to test the claim that this particular sample mean GPA is not unequal to, but is greater than 3.3. Okay, so when we run the test, we get the following results. We have a t-statistic of 8.366 with 69 degrees of freedom. Of course, that's one less than the sample size of 70. And our p-value is 0.0001. Now, because our significance level is 0.01, when we compare the alpha level of 0.01 to the p-value, we see that the p-value is much lower than the significance level. So it is very unlikely that we would get a sample such as this due to just sort of random variation. And so we have enough statistical evidence to reject the null hypothesis that the mean is 3.3, and to accept the alternative, which says that the mean GPA here in this situation is indeed greater than 3.3.